In this module, we will learn how the sun influences our near Earth space environment, creating space weather, and how it impacts climate. So, the space around us is not empty. Although the number of particles per unit volume is extremely low, nevertheless, there are particles which are in space outside the Earth's atmosphere, and these are fairly energetic particles, and the flux of this particle changes based on the activity of the sun. The electromagnetic environment around the Earth and planets, the radiative environment, for example, the flux of high energy photons also changes, and this is also governed by the activity of the sun. The solar wind, which is a flow of plasma from the sun, permeates the solar system, and although this is a very low density material, a low density plasma, it nevertheless exists and it creates dynamics which is visible and observed, such as geomagnetic storms and auroras. So, the space around us is not empty, and it is modulated by our host star, the sun, and this creates an environment which is variable, which is known as space weather. What you see here in this image is variable density perturbation in the near Earth space from the sun to about 3 astronomical units, which is well beyond the Earth's orbit, which has been measured through interplanetary scintillations, which is sensitive to the density of material which is passing through the interplanetary space. What you see here are solar wind and coronal mass ejection, which are very large scale storms from the sun perturbing the environment of the inner heliosphere, which contributes to variable space environment. Very extreme events such as flares and coronal mass ejections, which are related to magnetic instabilities within sunspots, also eject vast amounts of magnetized plasma into space along with high energy charged particles, which are also known as solar energetic particles, and these events are accompanied by intense X-ray and extreme ultraviolet radiation, which has significant impact on sensitive circuitry and sensors on satellites, as well as the upper atmosphere of the Earth, which is forced by this high energy radiation from the sun during this flaring events. We also know that there is a slow variation in the total solar energy output, and this slow long term variation is governed by the presence or absence of sunspots on the sun's surface. Therefore, the solar magnetic cycle in fact also governs the total solar energy output, which is in fact not a constant, although this was called the solar constant for a long time. This is a variable parameter, which is modulated by the amount of magnetic activity on the sun. So, this is providing various kind of pathways to force the Earth's upper atmosphere. In this image, you actually see what happens to a satellite detector during a solar storm, where many solar energetic particles essentially light up the detector, as you see in this particular image, which kind of tells you that there is increased flux of such high energy particles during the storms. So, the impact of space weather, which is due to the sun, is felt all the way from the space environment outside of Earth down to the ground level. In space, satellite operations, the sensitive electronics and sensors of satellites are subject to space weather. When a solar storm is passing through, the perturbation due to the storm also creates positional errors in satellites. For example, impacts the operation of GPS navigational networks. If you have human spacewalk going on during the solar storms, then astronauts may be exposed to severe doses of high energy radiation, which is not desirable, and therefore, it is important to be able to understand and predict this variable space weather out in space for protecting our satellite technologies. These storms also induce geomagnetic storms within the Earth's magnetosphere. These storms also, through magnetic reconnection, inject solar plasma into the Earth's upper atmosphere, and this changes properties of the ionosphere and creates ionospheric disturbances, which is important for radio communication, and therefore it is known that communication blackouts and disturbances can happen during this solar storm. Lower down, large conductors such as electric power grids and oil pipelines can have large voltages induced in them due to geomagnetic field fluctuations which are driven by the storms. And it has been documented in the past that solar flares have taken off large electric power grids. For example, in 1989 a big solar storm took off the Canadian power grid. So the impact of sun induced changes in our space environment are felt across various domains, starting from satellites up in space down to technologies that we rely on Earth, including satellite broadcast as well, mobile networks as well. So this is something that we are increasingly feeling because our modern society is increasingly dependent on such space based technologies, and we are now susceptible to the weather in space which is governed by the sun, and therefore it is important to be able to create the know-how to be able to predict the solar storms. Okay. Even longer term variation on the scale of decades or centuries. For example, the variation in the amplitude of the sunspot cycle through its modulation of the solar energy output or the solar irradiance can impact the climate system of planets. For example, this Maunder minima, this phase which is sort of denoted here by this big green circle sitting there between 1645 and 1715 AD, was a period when there were no sunspots on the sun and the magnetic activity of the sun died down. And this phase also coincided with the most severest part of what is known as the Little Ice Age, which is a documented phase of global cooling on Earth. And it is thought that the Maunder minima could have intensified the Little Ice Age, and people have been looking for, based on this, people have been looking for more direct links between specific events on the sun and its impact on the climate on Earth. A question that is often asked is, how does the sun impact climate? And this is through its modulation of the total solar irradiance, which is the total solar energy output as measured outside of the Earth over per unit area per unit time. What you see here are two plots. One is the sunspot number in red, and the blue one is the total solar irradiance measured via satellite since 1978. And you see a clear correspondence between the sunspot cycle and the energy output of the sun, right? And remember that this is the primary natural source of energy which is driving the Earth's climate. To give you an idea of how much energy the sun produces, in half an hour the sun provides enough energy which would drive the needs of all humans for a whole year, right? So there is enough energy in the sun, and the question is, does this variability also induce variability in the climate of the Earth? And in more recent times, the critical question is, does sun play a big role in the climate change that we have seen in the recent past? Of course, to do this, you have to really go back in history and reconstruct what the sun's activity has been in the past and correlate that with global temperature records reconstruction based on different kind of techniques. For example, one of the ways this is done is through looking at the abundances or the concentration of cosmogenic isotopes such as beryllium-10 in ice cores, which sort of provide a pristine history of the atmospheric conditions of the Earth in the past. For example, if you dig deeper down in Antarctica or Greenland, you will sample further back in the past, and if you for example take an ice core out, the deeper you go, the further in time you are sampling. You can use this ice core and chemical sort of spectroscopic analysis of this to figure out the various ratios of various cosmogenic isotopes such as beryllium-10. Now, the production of beryllium-10 in the atmosphere depends on the flux of cosmic rays, which is in turn modulated by the magnetic output of the sun. So, based on this set of inversions from the beryllium-10 concentration, which has been deposited at various times in the past, you can actually reconstruct what the sun's activity has been like in the past as well, and this has been done using this kind of techniques. And you can use similar reconstruction techniques for the global temperature based on the oxygen 18 isotope or carbon 14 deposits in tree rings. By comparing them, you can get a sense of what role the sun has played in past climate change. People have done this, and you have now records for something like 1,000 years or more even now. And what we find is there is certainly a link between the variability of the sun and its activity levels. For example, here seen in this red curve, which is the smooth sunspot number variation, which has been a reconstructed sunspot number based on this analysis that I just described, and then the global temperature record, which is provided in blue. And we find that in the long history or in the past, there has been a correspondence between the two, and the question is then, is the sun responsible for the global warming that we have been seeing in the recent past? And this is a field of active research, and the IPCC committee, Intergovernmental Panel on Climate Change, has looked at this very closely, and what it finds is that if you consider just the solar forcing, the solar variability, but not the increase in the greenhouse gas concentration, then you are not able to reproduce the observed global temperature variation, which is plotted here in the here in this curve, which is denoted by black line here. Only when you include both solar variability as well as the equivalent radiative forcing due to the increase in greenhouse gases, then you are able to reproduce this observed temperature rise. Critical analysis separately looking at these contributions can distinguish how much contribution the sun has in this, and the estimates range from 7% to 30%, which is fairly optimistic, but in general I think the consensus is that is certainly below 10%. The sun does not contribute more than 10% to the recent global climate change last century. And therefore, the conclusion then is that anthropogenic forces have been driving the recent rise in global temperature. This is still a very debated and a very intense field of research because of its implications for humanity. Given the importance of the impact of space weather on the Earth's atmosphere as well as our space based technologies, very mature space agencies like NASA, ESA, JAXA, which is the Japanese space agency, have a lot of missions which are up in space, which are looking at the sun and characterizing the sun Earth system and studying space weather. Some of the missions and the timelines are highlighted in this plot, and what is interesting to note here, and it's been pointed out, is that the Aditya L1 space mission, which is ISRO's first mission to observe the sun, is going to be launched in sometime in late 2020 or early 2021, and this is going to be a comprehensive space observatory which is going to look at the solar energy output, the near ultraviolet wavelength which drives climate dynamics, is going to look at the origin of solar storms and study the X-ray flux, the soft X-ray and the hard X-ray flux that comes out of the sun during solar flaring events. It's also going to image the movement of solar storms from very close to the sun's surface to about 3 times the solar radius, the outer parts of the corona. So, this is the most interesting region, because this is where the solar storms are accelerated and are born, and it also has instruments to make in situ measurements of the plasma at the location Lagrange point L1 in space. This is a point which sits close to the Earth, but in between the sun Earth, in the sun Earth line, which has a continuous view of both the sun as well as the Earth, and is an important point because whatever space weather hits the point L1 will subsequently come and hit the magnetosphere. So, the in situ diagnostics will include measurement of the particle fluxes as well as the magnetic field in the interplanetary medium. So, it is expected that this mission will generate new understanding for characterizing space weather. So, here are some resources, online resources that you can refer to for finding out more about space weather and climate. In this final module, we are going to look at star planet interactions and what this implies for habitability and life by taking the sun as an example. And this is important and a kind of very new research area, which is developing primarily based on our understanding gleaned from the sun, earth and the solar system, and which is now being applied to understand other exoplanetary systems beyond our solar system. So, just to recapitulate and to provide the motivation for this, we know that the sun is an active star and that its activity levels impact our near space environment and planetary atmospheres. Now, this is something that we have measured, we have observed and we understand given the current sun and the current solar system. But we also know that the sun evolves, and with reference to the first lecture of our model, we know that the sun evolves as a star, and this evolution is driven by various factors, including one important factor, which is the loss of angular momentum driven by stellar winds, which slows down the star. And when the star slows down, it's seen that its magnetic activity levels also are impacted by this slowdown, and therefore, it is expected that when the sun was young and a much faster rotator, it would have been much more active than it is at present. And these considerations have driven both theoretical as well as observational work to quantify how active the sun was in the past and how it has changed over time, and how the different possible activity levels of the sun may have influenced planetary evolution and planetary climates, and what this implies for habitability both in the solar system as well as other exoplanetary systems. Another very important thing that we also appreciate now is that the solar wind as well as the radiation of the sun play a role in the erosion of the atmosphere of planets. The way this happens is by the energization of the particles, the constituents, the atoms in the atmosphere of planets, and their erosion by interactions with the solar wind. And of course, this is something that is more drastic when there is no intrinsic magnetosphere of the planet, because if there is a magnetosphere, it sort of protects the atmosphere, and how it does so and what is its impact is something that we will soon find out when I outline some results from some recent simulations. But nonetheless, we understand that the interaction of the stellar wind, the magnetized stellar winds with the planetary atmospheres play a very important role in sort of the star planet interactions, right. To understand the impact of star planet interactions on the habitability of planets, we can take Mars as a case study. So, when Mars was very young, let us say we go back some 1 billion years into the age of the sun and Mars. Mars had a liquid core and a magnetosphere. So, it had a magnetic field which was protecting its atmosphere. The sun was also fairly active at this point in time, because it was rotating much faster. So, it is expected that the energy flux and the stellar wind density and fluxes would have been orders of magnitude higher than its current values, with much more frequent flares happening in the young sun. So, it is important for the atmosphere of Mars to be protected by this magnetosphere. In fact, we know that that Mars had an atmosphere at this point in time. However, with this evolution of Mars, the liquid core of Mars eventually became solidified, and due to this, the dynamo, the Martian dynamo, stopped working, and the fields decayed, and there were no large scale magnetic field in the in protecting the Martian atmosphere anymore. And this happened, I think, about 1.5 billion years into the history of this system. So, subsequently, the atmosphere of Mars was exposed to strong solar radiation as well as solar wind, and eventually now we find that Mars has really a very thin atmosphere rich in carbon dioxide, which is not really suitable for life, whereas much earlier, when it did have a magnetosphere, the Martian atmosphere was warm, moist, and perhaps more suitable for hosting life. So, the loss of the Martian magnetosphere and the interaction of the sun's activity with the atmosphere of Mars has led to this evolution, where now it is thought that at least at the surface and the atmosphere, Mars is inhabitable, and there may not be any life on the surface at least of Mars. So, this kind of gives you an idea how this coupled evolution of star planet systems can determine whether one can have life and a system which is habitable or not. So, if you look beyond the solar system, our own heliosphere, we find examples of astrospheres which are like the heliosphere, where we find that the wind from other stars have carved out a bubble in space, where it is protecting, this magnetic field is sort of protecting the planets from the interstellar medium and the cosmic ray flux, and they have these planetary systems which reside within these astrospheres of other stars, and these are known as exoplanets. And of course, there is a serious amount of research going on right now in understanding and characterizing these exoplanetary systems and how they interact with their host stars. So, one of the ways of finding out the activity levels, the magnetic activity levels of various stars, is to look at their X-ray flux, which can be measured with some high degree of accuracy, because it turns out, and as shown in this plot, that the X-ray flux, the X-ray luminosity, which is due to the amount of X-ray flux that is coming out of the corona of the stars, is strongly coupled through a parallel relationship to its magnetic flux in those stars and in the sun where measurements exist over a very large range of flux, which tells you that the amount of magnetic flux that a sun produces is directly related to is directly modulates its X-ray flux. Therefore, if you can measure the X-ray flux, then you can reconstruct the magnetic activity levels of the star. This has been done, and in fact, we have done this using observations of stellar X-ray data. And what you indeed find is, as the star ages, there is a very clear relationship of how the magnetic activity level and the X-ray luminosity, the X-ray flux from the stellar coronae declines with time, sun-like star ages. So, what you can then imagine is that when the sun was young, it had much more intense activity levels, much more intense high energy radiation than the current sun. And you have seen this plot that the current sun is really like in the moderate and low levels of activity, and a young sun would have had much more strong activity, which is orders of magnitude higher than the current sun. In fact, people have looked at the possibility of strong solar flares, not solar flares, but stellar flares from other stars, and much stronger than the sun, and these are known as stellar flares. And what is found recently, a few years back, a Japanese group published this result, where they provided evidence of quite a few stellar super flares whose energy can go up to about 10 to the power 36 ergs. These are immense storms, and some calculations show that if you have a planet with an atmosphere sitting close to a star which releases a super flare with this energy, the planet may lose a substantial part of its atmosphere to a single flare. It so happens that in the space age, such a super flare has not happened in the sun. There are ways of reconstructing based on cosmic ray flux past super flares, and we have not found evidence of the superflares in the last couple of billions of years in the sun's history. So, we do not quite know whether the sun has never produced such a strong flare or whether it did produce such a flare very early on. In fact, there is some recent evidence from in fact an Indian group at Physical Research Laboratory that maybe the sun had produced a superflare when it was about a little less than 1 billion years old. That is the only proof that there is of a superflare in the solar system. Nonetheless, this sort of points out that in those stellar systems where the stars are very active and which can host very strong superflares like this, the chances of life or habitability may be quite weak. Now, this is the kind of perspective that is based on observations and some qualitative understanding, but we can quantitatively simulate star planet interactions. The way we can do this, we can set up a system where we have a star and it has a certain output in terms of a stellar wind which has a magnetic field which is carrying with it. We can put a planet with an atmosphere in this sort of simulation box and then look at what the activity level, which is measured in terms of the stellar wind outflow and the stellar magnetic field content, how this activity impacts the planetary atmospheres, and this you can do with or without planetary magnetospheres. These are of course very intense and difficult simulations to do because you are resolving multiple time scales, multiple length scales. Very few groups in the world have this expertise. However, these are state of the art simulations which can tell you how intimately the output of a star determines the evolution of planetary atmospheres. Typically what is done in the simulations is you have a box with a planet sitting in it with or without a magnetosphere, and then you impose a stellar wind as a boundary condition, the certain content of magnetic field, and then you let it evolve and you observe in the simulation how the dynamics happens. So, here you see a simulation of star planet interaction that we have done. The Earth's magnetosphere is seen to be interacting with the solar wind which is magnetized to the observed level, and you see the formation of a bow shock on the day side which faces the sun, which is on this side. This is the bow shock, and this is the magnetotail where the magnetic field of the Earth's magnetosphere is dragged out into long distances and sort of reconnects further out away from the Earth, which is depicted here in this black circle. So, any atmosphere that is residing within this magnetosphere and the magnetospheric standoff distance, which is where the bow shock is protected by the magnetosphere. Anything that is outside that and out here in the stellar wind is not protected and can be pretty much blown away by the stellar wind. And it turns out how far this magnetospheric standoff distance from the Earth is determined by the wind speed and the magnetic field strength in the stellar wind. So, therefore, if the magnetic output and the stellar wind output of the sun or a star is stronger, we find that the magnetospheric standoff distance comes closer and closer to the Earth's surface. So, if the wind speed and magnetic field is weak, the magnetospheric standoff distance is here, but it is pushed closer and closer to the Earth when the wind speed increases, which kind of gives you a sense of how the activity of the star is impacting your atmosphere and how the magnetic field of the Earth is helping protect it. So, it is kind of a very complex dynamics involving the strength of the stellar magnetic field, involving the strength of the Earth's magnetic field and the extent of the Earth's atmosphere. There are fairly interesting dynamics that happen. We are finding that magnetic reconnection occurs in outer space between the Earth's magnetic field and the magnetized wind of the sun, and this reconnection actually helps in opening up some of the Earth's magnetic field and extracting out some parts of the atmosphere. For example, what you see is we have placed some atmospheric tracers here, and you see erosion of this atmospheric tracers through the solar wind. So, what this implies is when the wind and the magnetic field in the wind is very strong and magnetic reconnection is favored between the wind and the planetary magnetosphere, a significant loss of the outer atmosphere of the planet can happen. And when you do not have a magnetosphere, it is believed that this loss can be much more significant, and this can over a long period of time determine whether you end up holding on to your atmosphere or not, and which may in turn determine the habitability of the planet. There is also the possibility of injection of interplanetary species from the stellar wind into the atmosphere of a planet, and thereby providing a way of mixing the chemical species in the universe that has been produced in various processes, like for example, the supernova explosion, and dispersed in the interstellar interplanetary medium, of redistributing them and introducing them into planetary atmospheres, which is a fairly exciting possibility that is now being shown, that you can in fact have along certain paths of this reconnecting region between the magnetosphere and the magnetic fields of stellar winds, pathways may open up where interplanetary species may be introduced into the atmosphere of the planet. So, these all provide interesting pathways for the influence of the star and the interaction of stellar activity with planets. And to learn more about this, you can read this handbook on exoplanets, which has multiple different chapters on habitability and about the atmospheres of exoplanets. And in particular, what is highlighted here is this chapter on star planet interactions and what it implies for habitability in different exoplanetary systems. You can also read more about planetary habitability online, and you have a site which has been referenced here.